Have you ever questioned the nature of reality? Have you ever considered the possibility that what you perceive in your life could be vastly different from the underlying truth? This thought often springs from our experiences and observations of the macroscopic world we inhabit, a world governed by classical physics' predictable, understandable laws. It's a universe where cause and effect reign, where event follows logically from the one preceding, and where objects behave in a manner that aligns with our intuition. This is the world of atoms, particles, and subatomic phenomena, the domain of quantum mechanics. In this realm, the rules we've come to rely upon, the laws that seem so evident in our everyday life, no longer apply. Instead, they are replaced by a seemingly bizarre set of guidelines that defy our conventional understanding. This strange quantum reality is encapsulated in the quantum classical dilemma, a conundrum that has confounded the finest minds in physics for over a century. This dilemma essentially poses the question, why does the quantum world behave so differently from our classical macroscopic world? One of the most perplexing instances of this is encapsulated in the paradox of Schrödinger's cat, a thought experiment proposed by physicist Erwin Schrödinger. Picture for a moment a cat enclosed within a sealed box, in a state where it is simultaneously alive and dead. This peculiar scenario emerges due to the cat's fate being intertwined with the outcome of a quantum event. This paradoxical situation perfectly illustrates the weirdness of applying quantum rules to larger, visible objects. It forces us to question our preconceived notions about reality, and even prompts a significant re-evaluation of our understanding of the world. It urges us to ask if the quantum rules, so different from our everyday experience, could indeed apply to larger scales, fundamentally changing our perception of reality. But what if one could bridge the gap between the quantum and classical realms? This is a question that has haunted the minds of scientists and researchers for years. An extraordinary team led by a man named Sugato Bose wanted to address this question and unravel the truth behind it. They believed there might be a way to bridge this gap, and they were determined to find it. Sugato Bose is a man of immense intellect, with a keen interest in unveiling the mysteries of the quantum realm. His team, composed of equally passionate and dedicated individuals, shared his enthusiasm for this challenging endeavor. Together, they embarked on a journey that would hopefully delineate the fine line separating the quantum and classical domains. They began to develop a theory. The team suggested that perhaps we don't perceive quantum effects in our everyday existence due to an intriguing reason. They believed that the constant interactions of atoms with their surroundings might be effectively concealing their quantum nature, thus making it nearly invisible to us. In order to validate this theory, they knew they had to put it to the test. They needed an experiment that was as brilliant and creative as the minds that conceived it. After countless hours of brainstorming and meticulous planning, they devised an experiment that was nothing short of ingenious. An experiment that was designed to either affirm their hypothesis or send them back to the drawing board. To test this hypothesis, they devised an ingenious experiment. Their experiment, fondly referred to as Schrödinger's pendulum, involved an intricate process of suspending a minuscule nanocrystal of silica in a strictly monitored environment. The researchers used highly advanced, carefully calibrated lasers to manipulate the atomic structure of this solitary bead. If you could imagine, this bead, despite being so tiny on a macroscopic scale, is an enormous entity when compared to the usual quantum objects we deal with in the field. This tiny bead of silica was chosen for unique properties and suitability for the experiment. Every tiny aspect of this bead, including its precise size and structure, was meticulously controlled to ensure it met the desired criteria. The process required not just a great deal of scientific knowledge and precision, but also a deep understanding of quantum experimenters, in a carefully controlled environment, used the power and precision of lasers to nudge the bead back and forth. This motion was designed to mimic the predictable rhythmic swing of a classical pendulum, an image familiar to all of us. However, this is where things took a turn for the peculiar, and the quantum twist was introduced. In the mysterious and often counterintuitive quantum realm, the position of the silica bead remains a mystery. It exists in a state of uncertainty, its exact location unknown until it's observed. This is a fundamental principle of quantum mechanics, an enigma that continues to both baffle and intrigue scientists to this day. The role of observation is central to this experiment. It forms the basis, the backbone, and the pivotal point around which the whole procedure revolves. We start with a simple iteration, a basic experimental setup where we have a singular laser. This laser is meticulously aimed at the precise location where the bead is predicted to be. It might seem like a small thing, but the precision here is of utmost importance, as it sets the stage for the rest of the experiment. This laser then projects a beam of light onto the bead. The reflection of the laser beam off the bead forms an important aspect of the experiment. It is this reflection that exhibits, or rather represents, classical behavior. This is according to the traditional, well-established norms of classical physics. However, as the experiment progresses, it takes an interesting turn. The laser is introduced not just once, but twice. We create a secondary measurement, an intermediate one that adds another layer to the experiment. According to classical physics, which is deeply rooted in predictable patterns and consistent behavior, the outcome should remain largely the same. This is where the paradox arises. The quantum world, which is the realm we are exploring through this experiment, doesn't play by the rules of classical physics. Here, observation is not just a passive spectator. It doesn't just sit on the sidelines watching the events unfold. It actively influences the system. It manipulates and modifies the very nature of the system it observes. Yet in the quantum world, observation isn't just passive. It actively influences the system. In conclusion, Schrödinger's pendulum experiment stands as a groundbreaking exploration into the quantum classical divide. To fully comprehend the depth of this scientific endeavor, we must first delve into the history of quantum mechanics and its interplay with classical physics. Quantum mechanics, born in the early 20th century, revolutionized our understanding of the microscopic world, introducing concepts like superposition and entanglement. Classical physics, on the other hand, was firmly rooted in the macroscopic world, describing laws comprehensible to the human mind and observable to the naked eye. However, the division between these two realms of physics, the quantum and the classical, has always been a subject of intense debate among scientists. The quantum classical dilemma, as it's known, expresses the struggle of comprehending how the strange probabilistic behavior of quantum particles translates into our concrete reality. It is a question that has puzzled scientists for a century, forcing us to confront the fundamental nature of reality itself. Schrödinger's pendulum experiment then emerges as a beacon of hope in this perplexing riddle. By aiming to observe quantum phenomena at larger scales, the experiment challenges the established norms and the preconceived boundaries we have about reality. The experiment, in a way, is a bridge between the quantum and classical worlds, a bridge that could revolutionize our understanding of physics and perhaps even of existence itself. The experiment's groundbreaking nature extends beyond its immediate implications on the quantum classical dilemma. It provides a tantalizing glimpse into a future where our understanding of the universe isn't constrained by the scale we're observing. A future where quantum mechanics isn't an abstract discipline reserved for the particles, but a comprehensive theory that impacts our daily lives in ways we can't yet predict. The quantum classical dilemma may not be resolved yet, but thanks to efforts like these, we're inching closer to unraveling this cosmic riddle.